Okay, I guess most of us are back. What I'd like to do now is start into the rest of the material in Chapter 5. There's not very much left, and it covers virtual memory and an introduction to memory management, which is partly a hardware job, partly an operating system job. So what you're about to get here is a bridge into the operating systems course for next year. Some of these concepts will be, again, covered next year, but those that are here, your reward is it'll go a lot easier next year in operating systems when you've already seen it and understood it from CS-224. And operating systems is considered a challenging and hard course. It's a 4-credit course. And the other thing I want to say is everybody right now is complaining, oh, second year, second semester, such a hard semester. Look, all these things we have to do, you know. But I've got news for you. You are going to look back 1 year from now and say, oh, that was Hitchbürsche, that was Okadar Kolai, compared to the pain that you are suffering in third year, second semester, when you have data management, you have signals and systems, you have microprocessors, you have operating systems. So just, think of it this way. Right now, your troubles may seem big to you, but they're going to end soon, and they're actually light compared. It's making you strong to be able to handle even more challenging things, all right? So that's my encouragement to you is, oh, hold your project on this, you don't understand physics, and da-da-da-da-da. Yeah, I understand. I was a student myself, too. I didn't forget those years. I was very glad when I finally got my diploma and graduated and said, yeah, whew, no more tests. But you see, I came back. I've lived almost my whole life, except for 6 years working in industry. I've lived pretty much my whole life in school, either on your side of the desk or on my side. It's a great place to be. I encourage it. If any of you have that teacher spirit in you and you like the atmosphere of academia, I really strongly encourage you to continue your education as far as you can and instruct others. It's a great thing to be able to pass on what you know and inspire people. Anyway, let's start with a quick review of, okay, you know where we are. We're working in the memory section here, and we've looked at cache and main memory, but now we're just about to move to secondary memory and start focusing on disk-related issues as well. Okay, so we talked about how memory is managed, and we've worked a lot here on a compiler and programmer decide to move things between memory and registers. And we talked about cache a lot now, and when we said that there's a cache controller hardware that's going to be moving things between cache and main memory. And now we're focusing on this level of how to move things between disk and main memory and what to move and when to move and the whole issues there. But I think everybody can see that I'll have hits and misses when I ask for it here and have to go here, just like I'll have hits and misses when I ask here and have to go here. And there's going to have to be some coordination. It's managed by the operating system, and we call that virtual memory. The idea that if I don't find it here, it's there. Got it? This is memory. This isn't memory. But I'm going to treat it like it is. Yeah, okay. I'll include that slow magnetic stuff that spins and call it memory. It's virtual memory. Yeah? But I need help. The operating system management can't do it alone. We're going to give some help with some hardware called translation look-aside buffer. Okay? We're going to assist in hardware to help the operating system do this virtual to physical address mapping. These are physical addresses, and these are virtual addresses. Okay? We're going to map them so that these look like these. And then the programmer also does something when they access files. Obviously, you go to disk. We're going to have to, that brings things into memory as well. Okay, so here's our hierarchy. We talked about this before. Now we're focusing right on this zone right here, the interface between main memory and secondary. And the thing that we're talking about is called a disk sector or a page. A memory page is the amount that fits on a disk sector, and we move it up or we move it down. If I need to bring a page in, I bring it off of the disk sector and put it in main memory. If I don't want to kick it out, I kick the page out and I put it back on a disk sector. Okay, that's the idea here. And we know how this works. As I go this way, it takes a lot more time to access the next level down. And everything that's here is also included here. Everything that's here is also included here. That's the idea. Okay, what is virtual memory? It's using main memory like it was a cache for secondary memory. It's smaller, it's faster, it can include some of the frequently used items. Yeah, it's like a cache, but notice parentheses. Not a true cache, but like a cache. This allows us to have efficient sharing of memory and safe sharing of memory among multiple programs. All modern computers allow your program and your program and your program to be running at the same time. How is it that your program doesn't interfere with hers? How is it that none of you interfere with the operating system? The answer is we use this principle of virtual memory done with the method that we're talking about. Safe sharing and efficient sharing. Secondly, provides the ability to easily run programs larger than the size of physical memory. Can you see that if my program won't fit here, but it's allowed to also be here, and I can bring in pieces as I need them, then my program can be bigger than main memory. Virtual memory allows me to spill over. How would you like to have your program be only the size that could fit in cache? You'd say, no way, Jose. That's too small. Well, how about level 3 cache? Still too small for some big data and big code. How about main memory? Still too small for some big datas and some big codes. So let's even include secondary storage, in other words, disk. So it allows us to run huge programs. It simplifies loading a program in for execution because it provides for code relocation. Virtual memory says your code can go here in memory, here in memory, here in memory, and you don't even need to know about it. When you compiled it, when it was linked, nobody needed to know. It allows efficient loading or retranslation, relocation it says here. The code can be located anywhere in memory if we use virtual memory. Okay, you think your program starts at 0 and goes up to X, and then your data starts at X and goes to the end. That's fine, but we're going to relocate that, and maybe the code will start at 1,000 and the data will start at 1,000,000. We're allowed to relocate. Her understanding of it, the programmer's, is virtual address. What I just talked about is virtual address being relocated into different physical addresses, real addresses. Okay? Now what makes this work anyway? Again, the principle of locality. A program is likely to be accessing a relatively small portion of its address space during any period of time. So that portion we want to have in main memory, and the part we're not addressing we want to have be on disk. That allows us to share our main memory with many programs. Even if you have a big program, you're only accessing a small portion of it. So I'll give you enough memory to have high hit rates in that portion, and the rest of your code and data will be on disk. And that lets me use the rest of my memory for him and him and her and her and her and him. We can share memory, because you don't get to put your whole program in unless nobody else wants to use any memory. We'll share it. Just have the active portion. The part where there's high locality will be in memory. And when you move and say, now I'm doing something else, then we'll kick those out and bring in different portions of your program, code and data. Yeah, it's the caching principle, isn't it? Okay? Each program is compiled into its own address space, and we call that its virtual address space. And then during runtime, each virtual address is translated to a physical address. Okay, so the program says, I'm now at location 12. But that might not be at physical location 12. The virtual location 12 needs to be translated as I fetch to get the data or code that's at physical location, who knows what, 1,000,000 or 978 or whatever. So we're going to translate virtual addresses to physical addresses. All right, now that means that a program's address space is divided into these chunks called pages, as you can see. So the virtual address of a program is this page, this page, this page, this page, this page, this page. And as you can see, all the pages have space on disk, but only some of the pages have space in main memory. Which ones should be in main memory? The ones I'm using now. Which ones should be on disk? The ones I'm not using. That way I'll have hits on what I want, and I'll never ask for the ones that would cause a miss. But of course, once in a while, I'll ask for a different one and have to bring one from here, put it here. Program 2's virtual address space has got 5 pages. They all have to be on disk, and the ones I'm using regularly are in main memory. Notice 3 of them are in main memory, okay? So now main memory, 1, 2, 3, 4, 5, 6 of the locations are from these 2, and I have some empties that could be given to you or me or somebody else. I'm sharing main memory. Do you notice that the first virtual page doesn't go to the first physical page? In fact, it's been remapped to the last physical page. Okay, the first virtual page doesn't go to the first physical page. It's been remapped to the second to the last. See, that mapping function can be any way we want it. We could take your pages and put them all next to each other in main memory. We could take your pages and invert them and have them in opposite order in main memory. We could take your pages and spread them all over main memory. As long as when you ask for page 1, we know where to go and get it. and give you that code or give you that data. Or you want to write to it, we know where to write to it. There's a translation box in the middle. Program says, I want to go to the first page, the last location. And what we're going to actually do is go to the last page, last location. You notice that this block and this block are the same size. So a virtual page and a physical page in memory need to be the exact same block size, whatever that is, 4 kilobytes or 16 kilobytes or whatever. So when you're running through your code, you're going, I want this, I want this, I want this, I want this, I'm looping, I want this, I want this, I want this, I'm looping. I'm going for a data reference now. I'd like to go over to here and access the data structure. So what's really happening is, as you see, you're running through code here, and when you go here, you're accessing the data structure here. So you're actually in physical memory doing something similar, but the blocks have been reordered, and not all the blocks are in main memory because they don't need to be. All right, now I've said a lot. Do you want to react or question or make sure that you understand what I said there? You get the idea? This is a cache for this. The frequently used ones are in. The infrequently used ones are out. That's the first idea. Second idea is the program understands its address space, but we're going to call that virtual because we're not giving one-to-one correspondence to real memory. Therefore, since we're not, we're calling that virtual and calling that real, and we're going to have a mapping function in between. I haven't shown yet the mapping box, but every address gets translated into the real address. Virtual addresses come in, physical addresses go out. We need that translation box. That translation box is called a memory management unit, MMU, memory management unit. And we're doing it largely in hardware these days. It's on chip with all those billions of transistors that we have. But sometimes the need for that mapping gets so big that we spill over into main memory. So if it's on chip, fast. If it's go to main memory for translation, it's slow. So we're going to have a hit or miss issue there as well, aren't we? The chip stuff is the cache for the full thing in main memory. Hopefully we find the translation we want on the chip and it's a hit and it's fast. If not, we have to go to the main memory for the translation and it's slow. Just like going to cache versus going to main memory. So in a way, the on-chip translation cache is just like the on-chip data and instruction cache. But it's now translation cache for the translation box of in comes virtual, out comes physical address. Got those concepts? Is that okay? Any questions about that idea? Yeah.
This virtual address space is the property of
the program. Property of the program. The program says, I start at 0 and I go to X. Here's my code, here's my data. That's how the program understands itself.
This is a hardware like main memory or?
This? No, this is not physical. This is physical, this is physical. This is conceptual. Conceptual.
Is it the organization of the operating system or?
No, we're talking about programs. Program 2, program 1. I mean, the operating system is a program, but let's take that out right now. Let's just say your program is 1, my program is 2. You can count 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Your program's a little bit bigger than mine. Maybe it has more code or has more data. Whatever. Okay? Somebody does a homework for, CS-224 and says, wow, it's really big. I got a big program. And somebody writes a little, hello world thing for Java, and it's a really little tiny one. Whatever. It's a program. It has code and data. And it needs a space in memory.
What organizes them? What prevents them from?
What? Conflicting with each other? Such as? What? Such as this one saying, I want to read from here. Is that what you mean? See, this is blue. This does not belong to this. What keeps this one from going to this physical address? Is that what you're asking?
No.
No, what are you asking?
You said programs segment themselves from different virtual address space.
No, I didn't say that. I didn't say that. I didn't say programs segment themselves from different virtual address space. You said that, but I didn't say that. Yeah.
What is organized then? This.
Okay, try Turkish.
Program çalıştırıldığında.
Okay, this is yasak. We're not supposed to do any Turkish on camera. I'm a bad teacher, but he needs help, so I'm going to speak Turkish. Hello world. Merhaba dünya. Buyurun.
Hocam şimdi program çalıştırıldığında program 2 diye virtual address space oluşturuluyor.
Hangi program çalıştırıldığında?
Program 2. Program 1 vardı. Program 2 çalıştırıldı.
Yani çalıştırılmak, yani diskten belleğe yükletilmek ve organize edilmekten kastediyorsunuz değil mi? Tamam.
Evet.
Okay. Operating system'in işi bu.
Heh, onu soruyorum.
Evet.
Bunların ayarlanması...
Evet. OS. Yeah.
Okay.
Okay. Tamam. Good. That's easy. Yeah, I thought you were going to ask me something really, really hard. You were trying to ask that, I guess, but yeah, that's it. Yeah, the operating system will manage the virtual memory process. That's what we said on the previous slide. Let's go back a little bit here. This business is managed by the operating system. We call it virtual memory. It gets a little help from hardware, and that's the reason we're teaching it in this course. This is not a course on operating systems. You're going to have a whole semester course, but we are teaching hardware, and because these together, well, actually this too, programmer and operating system and hardware cooperate to do this. We need to talk about this part here, especially in the blue box, the TLB. So that's where I'm going with this, but we haven't got there yet. All right, any other questions about this? I know it's a new concept for you, but this is how multiple programs can share memory without interfering. That's one big thing. Okay, multiple programs can share memory without interfering. If you look here, that's 6 and that's 5. We don't even have 11 here. So the total size of this and this will not fit in main memory if I force all this to be here. And we all know that, don't we? If you want everything on disk to be sitting in main memory, you don't have enough money to buy that much main memory, do you? And we understand that fact, yeah? And if you want to have more than one program running at once, when's the last time you counted the number of icons that you've opened at the bottom of your screen? You're probably running 4, 5, 6, 8 processes at the same time. When's the last time you looked at Windows Task Manager and looked at the list of processes? Oh my goodness, it's 35 or 40 different processes open just when you start your computer. And then you open application programs. You know what I'm talking about. There's a lot of stuff going on in parallel. It would be a terrible straitjacket to just say, only one, no. When he finishes, then it can be your turn. That would be terrible. No computer would give any performance if we forced that straitjacket. So we're allowing, with this, multiple programs to have space in memory which does not conflict. And Turkair was saying, but how do we prevent the conflicts? And the answer is, the programs don't have to worry about that. The operating system does. For example, this program may think I start at 0 and go to 1000. And this program may think I start at 0 and go to 800. Peki çalışmaz mı 800'a kadar? The answer is no, because we're mapping them to very different physical addresses. So these logical addresses, 0 to 1000 and 0 to 800, are only logical addresses. They're not physical addresses. I tried to show that, and I think now that we have made that point well enough. Okay, so now, the starting location of every page, in other words, this is located here, and this one's located here. Who knows that? The answer is the program's page table. That's the translation. Starting location means physical location of page, which means virtual page. This is a page, that's a page, that's a page. Where is this page in physical memory? The one who answers that question is called the page table. It's the translation box that I referred to earlier. It's the page table. Okay, now, so we're going to translate a virtual address into a physical address. Can you see here that in this little example, virtual addresses have 32 bits, physical addresses have 30 bits. What could that mean? We have a 32-bit processor, so its addresses are 32 bits, but our physical memory is 1 gigabyte, so therefore I have 30 bits, right? Can you see how that would be? But this could be more, could be less. This is now bounces from this. This is part of the architecture. This is part of the actual implementation. So this could be big, could be little. So they're independent from each other. The main thing is to see that the virtual page size has to be the same as the physical page size. So if you're halfway through the virtual page, you'll keep the same number and be halfway through the physical page. If you're at location 0 in the start of a virtual page, you'll be at location 0 in the start of a physical page. So where you are in the page doesn't change. but where the page is does change. So what we're going to do is take this and translate it into this. No change here, big change here. All right, is that clear to everybody? What's the name of this translation box? Page table. Page table. Page table takes a virtual page number as an index, and the value stored there is the physical page number. Okay, let's go back. What's the physical page number for virtual page 0, 1, 2, 3? What's the physical page for virtual page 3? Physical page 0. What's the physical page number for virtual page 0? Seven, right? So at location 0, the data stored will be 7. At location 3, the data stored will be 0. Understand? Physical page in, virtual page number out. So the index is where I look. What's stored there is what I wanted to get, and it goes out. It's a simple lookup table. Any questions? So now we see that every memory request first requires a translation, an address translation from virtual to physical. Now when I have this, I can actually go to physical memory. So first translate, then go and get. Got that? First translate, then go and get. It's a two-step process now. So the translation is going to slow the whole thing down probably. And go and get might still have a cache miss, right? So go and get means go and try to get. Oh, we missed. Oh, we missed at the next level. Oh, so we can still have all that pain when we actually go and try to find it. Hopefully it's high in the hierarchy, but it might be low. But we're actually not going to talk about that anymore. We're on the other problem, from your point of view, the other problem, the first problem, which is translate. Got to do that. And what if that's a big translation table? Ooh, it won't fit in transistors. It'll have to be in main memory. So that means go to main memory to translate, and then hopefully don't go again for finding. Maybe find it in cache, but it's still now one memory reference and maybe two, right? Cache miss means it leads to two, but always at least one. So what do? We tried to speed up main memory accessing and get it into cache, and now you said, oh, but we always have to go anyway for translation. That's no good, so how can we speed up that? Have its own cache. Have the translation be a little memory hierarchy of fast access is quick on chip, slow access is you have to go to main memory for the translation. If this is big, it will not all fit on chip. So chip becomes a cache for the main memory part. Okay, you had a question? Can you feel that what I'm trying to do is motivate the need for this thing here? Translation, get the T, translation, look aside buffer. So buffer, that means it's high. Translation, so what I'm doing is heading for TLB, and I just gave you the motivation. TLB is going to be at the top of the little pyramid for here. The slow stuff will be main memory, the full page table. The fast stuff will be translation, look aside buffer. That's where we're headed. In a few more slides, we'll be there. But your question first.
Also, the virtual memory needs some space to keep the addresses. And where is it? Is it on the hardware or the space?
Okay. Virtual memory needs some space. Are you talking about these?
Yes.
Yeah, I just said to him, I'll say it again so everybody understands. This is a physical device. This is a physical device. This is only a concept. So it doesn't need any space because it's not physical. Only physical things need space.
We have some numbers, this virtual space, right? So
No, we don't have any numbers. In here I have code and data. And that code and data is either stored here with a copy here, or it's just stored here. This is a concept, and as you can see, all the concept is stored here, and some of them are also stored here. So if you ask, where is this? The answer is here. There's no third thing. There's disk and there's main memory. This is a concept. This is your program. Where is your program? Is it floating around in space? Yeah, it's in my mind. Yeah, it's on paper where I wrote the code. But where is it in the computer? Answer me. It's either on disk or it's in main memory. It's not some other third place, right? Where's your data? Main memory or disk? Where's your code? Main memory or disk? Come on. So this is the concept. And where do we map the concept? That's all this is showing. Don't think I need this gonna have to spend some money to buy this, and I'll have to spend some more money to buy this, and I have to spend some more money to buy this. No, no, no. This is not real. It's concept, only concept. Okay, are we together? Hey, come on now, focus. This is really hard stuff. Don't dalma, especially on back row, Suhail. I see you're drowsing off. I'm glad you came to class today, but try to give your very best attention to this. This is challenging stuff here. I realize that, but this is how real computers work. So if you want to be a computer engineer, you must understand virtual memory and this concept of paged mapping from virtual to physical address. I'm glad all of you are here today. I wish the rest of you were here too, but please now give your best effort and forget about Mayfest, and for the next few minutes, say, I want to learn this because this is good stuff. I know I need to know it. Don't, Hafif catch me. This is deep. Okay, any questions? I don't want to go on until we're sure we're okay. We keep getting questions, and obviously it's challenging intellectually. Merit? What this says is your answer. Each memory request first requires that we translate, and then we go and access memory. So, we used to just go and access memory, but now we translate and then go and access memory. So I think you can answer your own question. Won't it reduce the performance? It will reduce the performance, won't it? Yeah. Okay, so what have we got? We have a choice of no sharing, only one program, can't be bigger than physical memory, only one icon open, only one process open, but a little bit faster, or allow 50 users, allow a server, allow sharing, allow programs bigger than main memory, and a little bit slower. That's the choice. Yeah. Okay. So yes, there is a performance consequence. Now I'm going to show you, though, how to make that so small that we won't feel it. Okay. So right now it looks bad. First translate, then go to memory. Hey, Bidaka Hoja, just a few minutes ago you said when we go to memory, we don't want to even go to memory. We want to have a hit in cache. Now you're telling me first translate and then do that. It's artificial. It's an extra thing. No matter how fast you make it, it won't be zero. That's what it seems to be saying. And I'm going to try to make it be very low pain, very little pain. I mean, computer architects and 50 years of computer evolution. It's not magic. Don't watch, Uncle Will. I'm just going to show how the solutions can be done. Other questions? Yeah.
Why the length of the virtual page number differs when translated?
Well, like I said, this is virtual, this is physical. I don't know how much money you have. I don't know what kind of computer system you're going to buy. You buy a little one, you buy a big one. That's up to you. This is up to the architect who designed it. Yeah, this is a 32-bit machine, so our addresses are 32 bits. You want a 64-bit machine, you get a 64 bits. I don't know anybody that can buy 64 gigabytes of memory these days. It's too much money. So I mean, that and that do not have to be the same. I said earlier, this can be real short if you're very poor. This can be really big if you're really rich. That's a different business. That's how the motherboard is designed and the memory system and physical. This other one is architectural, ISA, instruction set architecture. We made some choices early about MIPS, so that's a design and that's an implementation. They're just bounces. That's great, they're bounces. It doesn't mean that you say, oh, I would love to have that processor, but I don't have enough money in my wallet, I'm too poor. Maybe when I'm 40 years old and I saved up all my money, maybe, suddenly that problem is solved. You as a poor student can actually get that architecture. You can buy a 64-bit chip and you don't have to buy 64 gigabytes of memory to go with the chip. It's a good thing, it's not a bad thing. All right. Let me ask you this question. In that picture right there, how big is the lookup table? Yani, how big is the page table? How many entries are in the page table? How many bits are there here? How many bits are there? 20. So how many different possible values can there be? 2 over 20. How many is that? 1 mega, yeah. So it's a table with 1 mega entries. Tell me what's stored at every entry. What's stored at every entry? Physical page number. How many bits is that? 18. How many bytes is that? More than 2. Say 3. Okay? So therefore, how many bytes is this page table? 3 megabytes, or 4. If we don't do 3s, then bigger than 2. Yeah, so 4 megabyte page table. Okay? So we just figured out the size of the page table. This is what has to be stored at every entry. This tells you how many entries you have. Okay. Weird.
This translation table contains the physical address to maybe address the currently 4 gigabyte memory. 4 gigabyte memory.
Yeah.
Maybe.
May.
And it
Not in this case. In this case, only 1 gigabyte memory.
yeah,
Yeah, okay.
And it will not give any physical address more than the capacity, more than the capacity of the
Right.
memory.
Right.
And I changed the memory,
Yeah.
main memory,
Yeah.
to 8 gigabyte,
Okay.
and
Great.
it starts giving physical addresses that it didn't give. While the
Yeah.
4 gigabyte main
Yeah.
memory
Right.
is computer. How it
Okay, the answer is found in the operating systems course. Obviously, remember, this translation table is managed by the operating system, but it's speeded up by and helped by the hardware. Speeded up in that this big table is going to have a little cache, and we hope to have a high hit rate in the physical transistor section of our chip and not have to go to the big table in memory. And therefore, the hardware part we're going to look at in this course is the translation look-aside buffer. But his question is, how does the operating system manage change? When the memory size is increased, how does the operating system compensate for that and change the page table so that everything still works? Great question, but wrong course. Great question, but wrong course. Okay. So I'm going to have to go on because we want to focus on the hardware focus of things. Good, I'm glad you're thinking though. I'm glad you're asking questions about how larger issues work. Can everybody see now that the early part of this course connected with application program software and compilers? This part of the course is now connecting a lot more with operating system software. Okay? And why is that? Because a computer is not just hardware, and a computer is not just application programs, and a computer is not just operating systems. A computer is the sum of the three. And you can't talk about one aspect without getting involved in the others. So anybody who thinks I can just learn programs and ignore operating systems and ignore hardware is foolish. Anybody who thinks I can just talk about hardware and ignore operating systems and ignore programs is foolish. And anybody who thinks they can just look at operating systems and ignore hardware and ignore application programs is foolish. It's an indivisible whole. You take courses in different areas, but what we want for you is to come out with a complete and integrated view of how these computers work so that you understand them from A to Z, top to bottom. It's not enough to just know Java and Java's class library, my friends. It's not enough. It's far from enough. Okay? So a programmer that doesn't understand operating system, doesn't understand hardware, will be a rather inadequate programmer. A hardware designer that doesn't understand user programs and operating system will be a rather inadequate hardware designer. Can they do some things? Yeah. Can they do the hard things, the good things, the challenging things, the best things? No. Okay? That's the point of CS-224, is to pull the pieces together. Next year in CS-352, which I'm also privileged to be a teacher for, we'll pull some more pieces together and we'll answer tough questions like Turker just asked. So I hope that you're seeing this four-year education is a lot of pieces that are gluing together slowly and forming a whole. Okay? Now, if you still say, but I don't understand how database fits in, and I don't understand how object orientation fits in, and I don't understand how software engineering fits in, and I don't understand how networks fit in, just be patient. Our goal is to help you understand how it all fits together, okay? And how to use it wisely and well for good purposes. Okay, let's go on. Let's call them. All right, now, if you ask for something from virtual memory that's not in physical, then it means it must be on disk. That's pretty clear from this slide right here. If I say, I want this one, and it's not here, it means it's over here. And we call that a page fault. A virtual memory miss, in other words, when the page is not in physical memory, you're going to have to go get it from disk. It's a miss. It's a fault. You missed in main memory. You're going to have to go get it from disk and bring it up. All right? Just like all our other cache behaviors, you had a miss. We call it page fault, but technically it's a main memory miss. And now let's look at the translation mechanism with a little bit of a different diagram. Here's the page table register. That's a register in the processor. You put a value in it that says, where does my page table begin? And so every process has a page table. So this page table that we are looking at here is just for your process. Every process has one. Where is this page table located? Main memory. Where is this register located? On the processor. Does every process have a special register for itself? No. There's one hardware register. Whose value is in that register right now? The process that's running on the processor. So if you have the processor and the CPU is executing your instructions, you have your pointer which says, there's my page table. If you go off and someone else comes in, they'll erase that, put their own, the pointer will be to their page table. Everybody's got their own page table. A page table per process. Okay? Now, one process right now has its page table pointed to. And we're not going to erase the page table and throw it all away and put a new one in. We're going to change the pointer to a different page table. That means that part of main memory will have your page table stored in it when you're a process, whether you're executing or not. And your page table will be stored whether you're executing or not. When you're executing, the pointer will point to your page table. When you're not executing, and you're not executing, the pointer won't point to your page tables. Let's go on. Here's the page table. It's in main memory. And you can see that there's a beginning address, but there's also the Birinji, Kinji, Chunju, all the way up down to the whatever. And each of these is a physical page number stored in that slot. So what's the virtual page number? It's the offset. Virtual page 0 points to here. Virtual page 1 points to here. Virtual page last points to here. The whole table starts here, but this is the offset, the index, the pointer into the proper place in the table. So how do you get this address? You take that plus that and add them together, don't you? Right? This plus this points to that. Is everybody clear on that? Yeah, you just have an adder to do that. This value plus that value equals that value, the address of that. When I go to that address, what do I get? Oh, yes, I get the location of that page in main memory. The physical address is stored here. The virtual address is stored here. But the physical address of the virtual address is this plus this, which is this physical address. This is main memory, and this is main memory. So part of main memory contains the page table, and part of main memory contains the code and data. Who manages this? Operating system. Who manages this? Program, right? It writes and reads its own data, fetches its own instructions. So the program accesses this. It never touches this. Only the operating system code is allowed to change things, write stuff. The page table is maintained by the operating system. Now, can you understand that? To make this fast, we put a cache and say, I hope I hit in cache. If not, I go here. How would you make this fast? How would you make this fast? Put a cache. The frequently accessed entries would go into the littler, faster cache. You'd say, I hope I find it there. If not, I have to go look in memory to find the translation. Cache for this. What do I want to have here? What do I want to have here? The frequently used items from here. All caches want to say, hey, give me the frequently used stuff and manage me in the right way, and I'll give you a high hit rate, and you'll see for very small extra money performance of the fast memory at cost of the slow memory. Are we with me? With me? So let's have a little bit of fast stuff here in transistors, which will give me very good performance and have a high hit rate, and I won't see the penalty of having this page table reference to slow down my performance. Give me some fast stuff here, and give me a high hit rate, and I won't see the penalty of going to this. Give me a high hit rate here, and I won't see the penalty of going to this, because it's so rare. Right? This is the principle of caching. This is what we're trying to do here in computer architecture. All right, the course is called computer organization, but what we've really gone into here is computer architecture. We're designing systems. We're designing systems in order to behave well. All right, got a couple minutes. I'll take some questions. I think we better not go any further than this. This is good stuff, but it's actually quite broad. We're not down at the transistor level anymore, are we? We're at the architect level, the Kushbakish level. But we're not just saying, oh, neguzel, neguzel. We're designing solutions to problems. We created a problem. Merritt pointed out, hey, didn't you just slow everything down? Won't that hurt the performance? Yeah. But it gives us so many benefits, we're willing to do that. And then we work on how to speed it up so that it doesn't hurt very bad. I'll show some more in the next class. All right. Was this useful today? Did you understand some more about how computers work? All right. You're beginning to understand virtual memory. You're beginning to understand how multiple processes could be in memory at the same time, how we could have processes that are bigger than all of memory because they allow disk to be, they're holding everything, and then the frequently used stuff is in main memory. So now you can see that I've got a hierarchy here, cache, main memory, disk. And I'm also going to put a hierarchy here. I'm going to not just let this be, oh, too bad, we have to go to main memory. I'm going to try to have a fast little cache here called translation look-aside buffer. But you can see that what's been done here is virtual page number and offset turns into physical page number and offset. That's the translation. Let's go back here. Yeah? Virtual page number and offset turns into physical page number and offset. How? Offset comes direct, and the virtual page comes through translation and becomes physical. Can we see that translation here? Yeah, the virtual page comes through translation and becomes physical. The lookup table is the translation. Too bad it's in main memory and big. Keshke, it was little and fast. Well, I can do something about that. But I've got to take a translation to get my physical address. Now that physical address goes to main memory. Or actually goes to cache, and if it's a miss, goes to main memory. Are you with me? So you see what happened here? This to this is the same as this to this. This box, the translator, is this right now. We're going to speed it up in the next lecture.
What are the first of the physical page table?
What's the purpose of the page table?
First bits. What are the first bits?
Oh, valid. Valid. Is it valid or not? 1 or 0. Can you see what happens? On the ones that are valid, we have a mapping from main memory. But on the ones that are invalid, we only have a mapping from disk. So the meaning is, if you want to go here, it's not in main memory. What did we call that on the previous slide? Page fault, yeah. So when you go and ask for it, the first thing you can find out is it going to be a page hit or page fault? Hit, 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 fault, fault, fault. So that's really bad news. It means you missed here, and you're going to have to go here. So this is irrelevant. Don't even bother to translate. You first got to get this into here, and then you can do this. Yeah.
If we transfer the value to main memory, first bits will be changed.
Yeah, if we bring anything up to here, we have to play some games and change the table too. Yeah. For example, if I take this block, these are all full, but let's say they're not, and I move it to here, then what am I going to do? Over here. I'm going to take this and put a 1, and right here I'm going to write 0, because I put it in the 0th place. So it says this now translates to physical location 0, and it's valid because I moved it up and put it in physical. You got it? So the operating system manages the page table. Operating system decides who goes here, and every time there's somebody moves here, we update this. What's the analogy to that we did earlier? We didn't do, but we talked about. Management between levels is the cache controller. Cache controller manages who moves up, who moves down, and knows which blocks are in the cache and which ones aren't. And on misses and replacements, it does business. This one also does business on misses and replacements. Only it's the operating system. It's a big software that has to run instead of a little small state machine. Obviously, little small state machines run really quick, telling the operating system, we had a page fault. You're going to run a lot of code, and you're going to spin the disk and wait. It's going to be a big deal. It's going to be a big deal to move a page off of the sector on disk and put it in. We hope we don't have a very high miss rate. Typically, miss rates for pages are 0.1 0, 0, 0, 1 or less. Not 99% hit rate, not 99.9 hit rate, not 99.99 hit rate, much higher than that. In other words, the hit rates are going to be very, very high, and the miss rates are going to be very, very low. That's the way good memory management is done. If your virtual memory system is a good one, you won't go to disk very often. All right. You've been very patient, very attentive, and real good questions today. Thank you all very much for being good students. Go out and have fun at Mayfest. See you on Tuesday.